In the previous video, we looked at the derivative of a function at a particular point, and we were able to take that point, x equaling whatever it happened to be, in general we'll just call it x equals a, and plug it into the limit function and solve. But that only gives you the derivative at a particular point. In other words, if you have your function f of x, it will give you the slope at, more like this, at that x value. But what we'd like to do is actually do the limit function, find the derivative at any point. In other words, we want to find the actual derivative function. So instead of using a, or whatever value a is, like I said, it could be 3, could be 2, could be 5, could be anything, we're going to find the general derivative function. And it's pretty much the same formula, except in place of a, we're going to just use x. So let's take the same problem we did in 3.1, and here I'll show you. In 3.1, we did 2x squared minus 5 at x equaling 2. So we were able to replace our a plus h, making it 2 plus h. We were able to find that the slope at 2 was 8. So this time we're going to do it a little bit differently. We're going to keep the general function. So we're going to use 2x squared minus 5. Now this does make it a little bit more complicated because we have more variables to work with here. Instead of just our h, we now have the x variable. So again, as we did in the last problem, to get started, let's summarize what f of x plus h would actually look like. So our original function, of course, is 2x squared minus 5. The x squared now the x has to be replaced with x plus h squared. So we need to simplify that before we go ahead and plug it into our equation, our limit equation. So I did that over here. So f of x plus h equals 2x plus h squared minus 5. We expand the binomial x plus h squared to get x squared plus 2x plus h squared. Distribute the 2, subtract the 5. And it becomes this long expression of 2x squared plus 4xh minus 2h squared minus 5. And that, as you can see, gets put in here. Now, of course, f of x stays the same. That's this piece. And it's just 2x squared minus 5. One of the things you want to be careful of, and you can see it here, you need to subtract 2x squared minus 5. So you need to distribute that negative across the 2x squared minus 5. So what we end up with is 2x squared plus 4xh plus 2h squared minus 5 minus 2x squared plus 5. What's nice is when you do this, and if you do this correctly, a whole bunch of things are going to cancel away. So your 2x squares cancel, your minus 5s cancel. In fact, in blue, you can see here we're left with 4xh minus 2h squared. Remember, because we are taking the limit as h goes to 0, we hope what will happen is our h's will cancel, so we no longer have that h in the denominator. And honestly, if that's not happening, go back and check your algebra and check your arithmetic, because you likely did something wrong. And you can see here my h's, I can pull out an h, and I'm left with 4x plus 2h. The h's cancel, and the limit as h goes to 0 of 4x plus 2h, now I can plug, I can plug my 0 in 4h, and I get 4x plus 2 times 0, which is 4x. This, again, is the derivative function. It's not the derivative at a particular point, it's the derivative at any point. And what's nice is, remember, in the previous problem in 3.1, we found it at x equaling 2. Once you get the derivative function, you can plug in any point and you can see we still get the answer that we got previously of a slope of 8. So here's another example for you to try. F of x equals 2x cubed. Again, when you plug it in, you're finding the derivative function. F prime of x is our derivative function. You're going to use the limit definition. Keep in mind on the test, I am going to ask you to do one limit definition, general, to get your general derivative function. So you have the limit as h goes to 0 of 2, x plus h cubed, because my x has to be replaced with x plus h, then minus your 2x cubed over h. This part I expand out on the side. This one gets a little messy because it's quite long because we have to expand a cubed a binomial that's cubed now. But if you do everything correctly, again, what happens is we are able, a lot of things cancel away. And then when you pull out your h, you are left with 4x squared plus 2xh plus 2x squared plus 4xh plus 2h squared. I strongly suggest you kind of stop the video at this point up here and try this on your own to see if you can get the exact same answer. Because when we then plug in our 0 for our h's, we are left with a 4x squared plus 2x squared, which gives us 6x squared. And our derivative function is 6x squared. So for a third example, I'm giving you the function square root of x. You might think this one's going to be much harder, but actually it does not end up being that way. Again, I suggest you stop the video at this point and try it on your own. And then, when you're done, start the video back up, unpause it, and see if you get the right answer. And here's the work done for you. So we have, again, place of x, it's x plus h, all under the radical, minus square root of x plus h. You have to, in this case, we learned in chapter 2, we can use a conjugate to remove these radicals. So we're going to multiply it by the conjugate of radical x plus h plus radical x plus h plus radical x, because this whole fraction reduces to 1. And when I multiply x plus h, radical x plus h plus radical x plus h times radical x plus h, I just get x plus h. And the radical x is minus x. So you can see a lot of things start to cancel away. My x's cancel. I'm left with h over h times that conjugate. The h's go away, and I'm literally left with 1 over that conjugate we multiplied. But when I plug in my 0, I got 1 over radical x plus radical x, which is simply 1 over 2 radical x. So let's summarize all of these derivative functions we found. F of x was 2x squared minus 5, and we said the derivative function was 4x. When f of x was 2x squared, 2x cubed, our derivative function was 6x squared. So just looking at these two, what you want to look for is that pattern. So of course 2x squared, we now know there are kind of shortcuts, I'll call them, to finding our derivative. We don't have to go through the entire limit definition. And we now know that the derivative of 2x squared minus 5, because you can take the 2, the exponent, times 2, you get 4x. And of course, the derivative of 5 is 0. And 2x cubed is 6x squared. So if I gave you over here 5x to the 4th minus 3x squared plus 2, we would get 20x cubed minus 6x and then plus 0. The same worked for the radical. You just have to learn to rewrite your radical as an exponential function. So the radical becomes x to the 1/2. So again, I multiply the 1/2 out front, and then I have to do 1/2 minus 1. So it's x to the negative 1/2, which is 1/2 radical x, which is exactly what we got when we applied our limit definition. So that's how we find our general function. Now, and the other thing we want to look over in this particular example is the graph of the derivative function. And a great exercise for you is to go into Desmos and go ahead and plot both the function and the derivative function. Desmos will do it in another color. And if you play around with that, you'll see the relationship between a function and a derivative function. So for example, if I just had the function, let's suppose it went like this. There's my f of x function. From that, I can sketch the derivative function based on what I know about derivatives. Derivatives are the slope at a given point, correct? So when I look at this particular function, one of the first things I want to look for is, hey, where is my slope a horizontal line? In other words, where is my slope 0? Because if my slope is 0, that means the derivative function at that value of x has to hit 0. Then I want to look at when my slope is negative or positive. So think about that. Up from negative infinity up to here, isn't my slope, whoops, I lost my function, sorry about that. There we go. Again, from negative infinity up to this point where my slope is 0, isn't it always negative? That means it has to be below the x-axis. Then between this point and this x value, it's positive, so it's above the x-axis. It has to turn around and come back. And then it's negative again. And we see that this original f of x, which is likely a cubic function, becomes more of a, it's not the best drawn function, more of a parabolic function. So again, a good exercise to do right now in Desmos is just to play around with a couple functions, even this f of x function, and then plug in the derivative function and see if you can identify the relationship between the derivative function and the original function. Because on the test, you will be given a function. So here's a simple one, a parabola, and you will be asked to sketch. Now, when I say sketch, what that means is I don't like in this one we did over here, I don't really care how far up you go at this point. We'll get to that in chapter 4. So when looking at this parabola over here, one of the other things you want to understand the relationship of, a parabola, of course, is a function that has an x squared. So the derivative of a parabolic function would have to be a function with the highest exponent of 1, so it should be a linear function, where our original function here is likely an x cubed function. We ended up with a parabolic derivative function. So let's take a look. Again, there's our 0. That's where our derivative function is going to go through 0. We are a positive slope before that, and then a negative slope after it. What you're not going to get is exactly the steepness of that slope when you make your sketch, but as long as you understand that it's positive, meaning above the x-axis, and then negative below the x-axis. Also note that this linear function overall has a slope that is negative because our parabola is a negative x squared parabola, so it would end up with a negative derivative. Anyway, the best way to be able to sketch derivative functions is to go into Desmos and really type in some random functions, see if you can sketch out the derivative function, and then type in the derivative, finding it algebraically into Desmos, and see if you got it right. Thank you.